Welcome back, ladies and gentlemen, to our next double bill. Gerard Barron is the CEO of DeepGreen Metals. He's on a mission to help wean humanity off fossil fuels and transition to a circular resource economy. He's a seasoned entrepreneur with a track record of building global companies in battery manufacturing, media, and future-oriented resource development. His guest, Bjarke Ingels, founded BIG, Bjarke Ingels Group, in 2005, after co-founding PLOT Architects in 2001 and working at OMA in Rotterdam. Named one of the 100 most influential people in the world by Time in 2016, Bjarke has designed and completed award-winning buildings globally. Alongside his architectural practice, Bjarke has taught at Harvard, Yale, Columbia, and Rice University, and is an honorary professor at the Royal Academy of Arts School of Architecture in Copenhagen. Please welcome Gerard and Bjarke.
Thank you very much. So giving form to the new frontier. We live in a world that has been changing for 4.5 billion years, and it's important to understand our planet's history because it shapes the stories that we tell ourselves about our home planet and our future on it. Earth's biography has been a roller coaster ride. It was a hellish start, bombarded by space rocks, 4 different atmospheres, several different oceans, 7 supercontinents so far, a snowball coma and a spurt of biological innovation, punctured by 5 massive die-offs. And our planet is habitable, but it's not necessarily safe. Atmospheric revolutions and ecological catastrophes do happen despite the planet's biogeochemical checks and balances. So our planet has a track record of getting off kilter and getting tangled in positive feedback loops, and then taking millions of years to regain a form of equilibrium. And this is without human help. And humans entered the world-changing business about 10,000 years ago through agriculture and husbandry and through indigenous tech. And some of us are still trying to wrap our heads around the fact that even the Amazon is not the pristine natural ecosystem, but the artifact of indigenous tech. And through Columbian exchange that homogenized the food we eat, but also exported a truckload of new diseases that wiped out most of the American indigenous populations. And then, of course, the more recent and familiar industrialization, where we have taken it up a notch. Our world is still changing to its own tune, but now within the blink of time, we humans are changing it too, adding 100 times more CO2 into the atmosphere per year, more than all the planet's volcanoes. The oceans are more acidic than they were a century ago, and sea levels are rising 30 centimeters per century after being stable for 7,000 years. And we're moving 10 times more rock and sediment than all the world's rivers. And the species extinction rate is 1 to 10,000 is higher than normal. We have run up against several planetary boundaries, and we may have already triggered our planet's infamous positive feedback loops. So our planet and even life on it will be fine. Human future, on the other hand, is not assured, and we may very well be the most endangered animal on this planet. Yet, a simple U-turn is not an option. There are more than 7 billion of us, and we're expecting to add another 3 billion people this century. We need to provide for us all. So simply going back to pre-industrial tech is not an option. There is no going back. There is no stopping. We have to figure out a different way forward on the move. So we know what we must do. When Stuart Brand started his Whole Earth catalogue in 1968, its front matter said, "We are as gods and might as well get good at it." So the focus then was on the green movement, largely on protecting the Earth from humankind. 40 years later, Brand wrote a different book arguing that now we need to protect humanity's future on Earth. We have to get good at it. How? Well, it's not rocket science. It's actually much, much harder. Our planet got its cosmic endowment of energy and matter, and then it had over 4 billion years to put it all together and experiment. And we've been around for a minute, had a few seemingly ingenious ideas that allowed our population to balloon to over 7 billion. And now, with barely 1 minute of experience, we have to figure out a way to integrate our systems into our planetary system. That requires new realism. we need to do much more homework and change our operating ethos. And on the homework front, one point of departure should be deep care for life in general and humans in particular. Hatred and self-loathing, now so rampant in the green movement, is not going to solve problems. Understanding whole earth systems is now a non-negotiable. And we desperately need temporal literacy. We need to know our Earth's past and our future history. Looking at everything through the lens of human timescales is warping our understanding of the world. And science is a process of moving from wrong to less wrong explanations. I see science being turned into dogma and misused on each side of any debate. Of course, if you accept that science might not have all the answers yet, and that some of the answers might be wrong, it pits us with our least favorite anxiety-inducing state, uncertainty. We need to grow stomachs for uncertainty. At last, but not least, we need to have courage for trade-offs. We will not get out of our current predicament without causing more damage. The question is, how do we minimize it? So as a civilization, we want to get off fossil fuels, but the clean energy transition is a wholesale planetary rebuild and upgrade. And it turns out to be very metal intensive. We know that building offshore wind is much more metal intensive than generating power from coal or natural gas. Building an electric vehicle requires much more metal than conventional metals. So there's some good news, and the good news is that these metals are infinitely recyclable. We have a perfect techno-nutrient for the EV technosphere. But the bad news is we do not have enough metal in stock to be able to drive this clean transition. So what about the environmental and social impacts? And so we focused on the impact of one electric vehicle. And you'll need a lot of copper and nickel and cobalt just to build one electric vehicle battery. In fact, to secure those metals on land, we'll need to mine an area about the size of 10 car parking spaces. And we're going to disrupt about 570 kilograms of contained carbon. Why? Because we mine it from open pit environments like this. And as we destroy those dense forests and remove all of that topsoil, we release an enormous amount of sequestered carbon. And of course, by taking away that land and destroying everything on it, we take away the opportunity of sequestering more carbon as well. So restoring all that land after half a century of mining is, if it's ever done at all, of course, if the mining company hasn't disappeared, takes a Herculean effort. Takes about 65 years after we replant rainforests. They still only absorb 40% of the CO2 compared to the original forest. So full recovery is modeled to take about 4,000 years. So the top metal producing countries currently are also very areas rich in biodiversity: Chile, Indonesia, South Africa, and the Congo. And we're still having to deal with issues like child labor, which is prevalent in the Congo, where they mine cobalt in these artisanal mines. So going back into what it takes to make our one battery, the mining sector is by far the single biggest source of waste on our planet. With the average grade of mine today is about 0.5 of 1% for nickel, for copper, sorry, and about 1.3% for nickel. So to make that battery, that 155 kilograms of battery material, we'll have to disrupt about 64 tons of material on land, made up of overburden and metal-bearing ore. And of course, what we do with it is we put it into piles like this. Even worse, we sometimes dump it into rivers. Land-based ores have lots of deleterious elements like arsenic and mercury. They need to be removed, and that generates tailings. These tailings have to be kept forever. Sometimes it doesn't work. They burst and wipe out communities and human lives. Or even worse, in places like Indonesia, which is the leading nickel producer, they're starting to dump tailings into the deep ocean, into the coral triangle, which is home to almost 80% of all coral reef species. But they can't build tailings dams because of where they sit on the tectonic plates. So here are the biggest footprints associated with producing those 4 metals for just one electric vehicle battery. 13 tons of CO2 emissions, 45,000 liters of water, 64 tons of waste material, and 58 tons of toxic material. And if you find that all unsettling, well, what happens when we scale it up? So recently we published a white paper focused on the footprint, the environmental footprint, if we make 1 billion electric vehicle batteries, which is where we're heading, from terrestrial-based ore bodies compared to from our ocean metals. And that will generate around 13 gigatons of CO2 emissions, not to mention 64 gigatons of waste material. And if we think about our target of keeping global warming restricted to 1.5 C, that will take 13 gigatons out of a pretty small budget of 222. So the good news is metals can be recycled, but the bad news is we don't have enough of them to meet the demand of the clean transition. And we also have to supply, of course, metals for the continuing industrialization of the developing world and growing population. So if we could take a step back and take a planetary, but even perhaps solar system perspective, what's the smartest place to get virgin metals? Well, what if we found an entirely new type of resource where we didn't have to remove the forests, where we didn't have to take away all of the topsoil, and we didn't have to drill or blast to get to the metal-bearing ore, but instead we came across this very large, abundant gathering of rocks just lying there. It could be in an undiscovered desert, but in this case it's on the bottom of the abyssal zone in the Pacific Ocean. And these rocks contain the metals that we need to build these batteries: nickel, copper, cobalt, and manganese. And the good news is they don't generate any waste material. They also don't contain deleterious elements apart from very fine trace levels, so no tailings. So we use 100% of those rocks or nodules, so zero waste. And these things make a huge difference. If we produce those 4 metals just for one EV battery, we'll use 4 times less metal-bearing ore, or a tenth of the material if we include the overburden. So 6 kilograms versus 6 tons versus 64 tons. And we can massively compress those impacts, including reducing CO2 emissions by more than 90%. We can eliminate waste, we can eliminate tailings, and we can only use 10% of the amount of water. But there are 2 issues that remain problematic. One is seabed use, and the other is the impact on biodiversity. But these rocks sit on the abyssal zone, on the bottom of the ocean, and that has some advantages as well, because we don't have to build fixed infrastructure. We don't have to build deep water ports and railways and roads and power and communities to house our people. So this is where we are in the Pacific Ocean, about 1,000 miles off the coast of Mexico. And currently, there's around 1.1 million square kilometers under license. Keep in mind, the ocean is 360 million square kilometers in size. So we're talking about an area 0.3 of 1% of the ocean floor. And already the regulator has put aside 1.4 million square kilometers into protected areas, areas where nodules will never be collected. And if we look at the full LCA impacts from cradle to gate, we kind of knock the ball out of the park on every facet. We massively reduce CO2 emissions. We don't unleash any sequestered carbon. Carbon is locked in the deep ocean, and we have no impact on releasing it. We don't generate waste. In fact, the only red bars are we use more seabed, of course, and we're studying the impact on biodiversity. And we'll also need to use some more ocean floor. In fact, if we'll have to use around 500,000 square kilometers just to make those 1 billion electric vehicle batteries. And if you compare that to land use, we'll use 500,000. And if we were to go mining on land, we would use 156,000 square kilometers. But the beauty of our deposit is it's 2D. And so that has some impacts. For example, we have 15 times less carbon stored in deep sea sediments compared to the average biome on land. And there's 300 times less biomass stored in the abyss zone. And becoming more granular, if we measure life as biomass, the average biomass per square meter is 13 grams. And 70% of that is bacteria living in the sediment, which we won't destroy. We'll give it a bit of a tumble if we pass over it, but it'll stay there. And we compare that to the biomass on land where we're currently mining our nickel, and the biomass there is more like 20 kilograms per square meter. So wildlife impacted by mining on land is very, very different to the wildlife that'll be impacted in the deep ocean. There are many more species. They're on land. They're usually much bigger and more varied. They have complex behaviors and complex intelligence. They have a complex coevolution, and they're much, much more abundant. And we're really studying megafauna, but we will disturb that megafauna and as our robots pass over it. And so our studies are around the impacts. What are the impacts of removing the nodules? But the good news is we can mitigate that several ways. Firstly, the regulator helps by putting aside large areas not to be touched. Secondly, we can have no-take zones where we don't take all the nodules and we set aside areas. The other thing we discuss or study is the sediment. What happens to the dust? And think of it as driving down a dirt road. How far does that dust travel? And the good news is on the ocean floor, the particles tend to flocculate together, so they don't travel far at all. And then finally, where do we return the water? Because we separate the nodules, we pump them to our production vessel, and then we return the water that went up the pipe. But science will tell us where to return that. And that science involves more than 100 specific studies that will form part of our environmental impact assessment. With the help of some of the leading institutions around the world. And it's the largest, actually, ocean science program ever undertaken from seafloor to ocean surface. And we are already working on developing an adaptive management system that will allow us to do real-time monitoring of the operations and share it with our regulator and civil society so that these potential operations would be physically remote, but this does not mean they're out of sight or out of mind. We believe it's important that the impacts of our global commons can be observed and monitored by interested stakeholders. And a major advantage of having a 2D resource is that it's a thin, tiny top layer, like between 2 and 5 centimeters, spread over a very wide area that we disturb. And it gives us a lot of freedom to adapt, and we can go around ecologically sensitive areas, and it just provides us enormous advantages over the known practices. But the ultimate adaptation, of course, is to stop these operations as soon as we have filled up the inventory. And the best way to do this is to stop thinking of metal atoms as a consumable and start thinking of them as a service. These metals have been forged in supernova explosion billions of years ago, and they're still around, and they will continue being around for billions of years. But we do need to stop digging them up and then misplacing our old atoms and returning to dig up new atoms. Ideally, we would dig up just enough metal atoms to make what we can't make out of the current pool. And this pool becomes our metal commons. When you buy an electric car, you don't get to own the metals the car is made of. You merely have the right to use the structural and physical and chemical services provided by these metals. And you have the obligation to return these metals at the end of life to the metal commons. If you lose them, you'll have to pay for it. Metal is not a consumable. It's a service. And we have a short video.
Energy from the sun and wind is replacing fossil fuels to power the transition to a sustainable future. We need batteries to store this energy. Batteries are made from metals such as cobalt, nickel, copper, and manganese. Until now, we've been mining the earth for them, digging deeper and wider for lower quality ores. Nature disappears. Humans suffer. Earth suffers. But there's another way. Polymetallic rocks contain rich concentrations of these base metals needed to make batteries. As stewards of these rocks, we've partnered with top ocean scientists to baseline the environment from seafloor to surface and study the impact of collecting them. If we use them to make 1 billion electric car batteries, we can dramatically reduce our environmental and social impact for the whole planet. We're building a world where metals are not mined and dumped, but rented and returned.
So maybe just to give you a quick idea about this, let's say, human-made ecosystem we are designing for this new industry. We're essentially designing a fleet of offshore vehicles where we're trying to sort of minimize the impact as much as possible, creating these kind of streamlined collectors on the ground. Together with marine engineers, we've designed the shape of the hull with a lip so it minimizes the plume that is blown up to minimize the impact on the environment. The collected material is pumped up to a production vessel at the surface where it is sorted, and then the water is pumped back below the sunlight zone to minimize impact on the local microclimate. You can see the entire fleet has been designed from scratch. All of them are white above grade to minimize the thermal expansion of the steel. We basically took a standard drilling ship and sort of redesigned it to optimize its design for the specific purpose, making it as small as it can be, using an X-bow to reduce the impact of the waves, introducing the idea of a photovoltaic roof that protects the environment on the surface of the ship, and produces 7% of the power that the ship requires. It can still open up to access the materials on it. So here you see the production vessel, and you can see that the paint is only in the waterline to minimize the soiling. Then we're designing this little fleet of E-cats and helicopters to go with it. So here inside the production vessel, together with the production vessel, you have the support vessel, which is where the moon pool is, where you can sort of extract and service the collectors. And also you have the shuttle vessel that essentially contains a series of compartments for bringing the raw material back on shore. So you can see in many ways we're trying to sort of make the most optimal performance, and as a result we're creating this kind of new language for an entire new industry. And then of course this kind of offshore fleet collects to the onshore metallurgical plant, and what we're trying to do is take something that normally looks like this, a kind of industrial wasteland, and make it more like this, a clean technology that can actually have positive social and environmental impact on its neighborhood. The nodules are turned from this into 100% usable materials. This is the kind of array of outcomes, and essentially it's a linear process that we have organized like a single loop. So the entire facility is a loop underneath a rain cover. So outdoor, naturally ventilated, you have the materials arriving, then you have this kind of linear loop. You have circulation for the staff, circulation for visitors, and the sort of circulation for the material as it departs to be put into good use. So we're imagining a onshore transformation plant that has a completely different impact and vibe than a typical sort of resource processing facility. So here you see a visitor learning about how the nodules are turned into usable materials, a staff sort of overviewing the production and the facility at night. And maybe sort of as a last element, what we're looking at for the future, since the fields are 2,000 kilometers from land, we're looking at designing community vessels where the offshore workers can actually live, where you can have local farming, where you can have sort of a desirable lifestyle in sort of synergy with the surrounding nature. So all in all, we're trying to imagine, rather than the sort of industrial plants that we know today, a kind of new fleet of gentle giants on the sea and on land, where we sort of imagine this kind of social infrastructure for the transformation of our energy towards renewables that can actually coexist with sort of adjacent forms of living. We can imagine plants where the car batteries are produced, or even people living and working adjacent to this kind of new generation of clean industry. So maybe on that note, I realized that we are practically up for our time.
Okay, thanks so much for that, guys. Let me ask you a few of our audience questions before we wrap up. Bjarke, you've spoken in the past about how, although each place has its own unique culture and climate, designers always need to have a global view and gather ideas about the best lived practices to inform how they design their local world. Can you tell us about any innovative practices which you think should be shared?
In this particular case, or in the world in general?
Let's say both in this particular case and the world in general. Why not?
I mean, I think what this project is a part of is that I think part of the source of the climate crisis we are in on the planet is this kind of global mindset of thinking about front of house and back of house. So you can say the front of house is all the nice things that we put great care into, you know, where we live and the lobbies, and, you know, and then there's the back of house, the parking lots, the landfills, the industrial wastelands that we somehow leave behind. And I think with climate change, we've come to realize that there is no back of house. The whole thing, the entire planet, is our only house. And what we're looking into is, in a way, trying to think about our industry, our infrastructure, as part of this kind of more holistic mindset, that we should put the same amount of care into where we get our resources, into the sort of processing plants, as we put into maybe our kindergartens and our schools. So in that sense, I think this is the kind of mindset that this next generation is going to be looking into, and it's the kind of mindset that I think can get us out of the climate crisis.
Thank you. Here's a question from Ingrid for both of you. We talk a lot about our sustainable future, but we need a sustainable present. Do you think that there should be more drastic action done to save the environment, rather than coming up with similar alternatives to our current way of life?
Well, I'll go first, but I guess if you saw in my first part of my presentation, yes, but there's, as I also said in my presentation, there's no going backwards. There's no U-turn available. And so what we need to have are more grown-up conversations about the reality, about the situation we find ourselves in, and what the meaningful solutions that can make an impact on the crisis we find ourselves in. And fossil fuels is one of them, you know, and we can't save ourselves from fossil fuels by simply consuming less. We have to transition. We have to create an entirely new ecosystem using renewable energy and batteries. But then we have to face up to the reality of, where do these things come from? You know, you can't want something and not be prepared to say, what are the impacts? And then we need to have grown-up conversations about comparing those impacts versus the known impacts of what we do already. And then society can make more informed decisions.
Yeah, like I also think that what's maybe new and relevant is that today, compared to 50 years ago, we do actually have tools that give us updated knowledge about the entire planet. So I think this idea of like only looking within your little frame of mind, you have to somehow think of everything you do, even if you act locally, you have to have this kind of global mindset, and therefore I think it is incredibly relevant to start thinking about, in a holistic way, where do the resources for this transformation of our entire economy towards renewable energy, where do they come from, and how do we make sure we have enough of them, and how do we make sure that the side effects of getting enough of these resources to make enough batteries are not more detrimental than the benefits of getting the batteries. And I think this is in this space that the DeepGreen really starts playing a serious role.
Okay, time for just one last question, again to both of you. What gives you hope for the future?
People that are not prepared to accept our current situation. You know, what gives me hope is humankind and our curiosity and our willingness to look for answers. And so humans give me hope for the future.
Yeah, and I also think, like, just in my lifetime, until I was 15, the Iron Curtain was still up, and I think we were all concerned about, the potential of nuclear holocaust and the kind of power struggle with the Soviet Union. And I think the new generations have actually grown up with climate crisis as something looming over them, which makes them hell-bent on dealing with it. And I think in that sense, just like you can say, if the entire world has been capable to varying degrees of success, but at least with very, very firm and resource-intensive action to deal globally with COVID-19, I think as soon as we are out of that, we're ready to take on the true challenge, which is right ahead of us.
Well, let's hope so. Gerard and Bjarke, thank you both so much.